Hello, good afternoon. Can you guys hear me? You can type in the chat box. Yes, okay, excellent. Thank you. Excuse me. So first of all, go to chat course and download your today's quiz, but you have until 4:30 today to finish and upload. So here's the plan for today. And first of all, we are going to study Routh-table again and run through some examples. After that, we are going to go through a PID module. I'm going to show you. So this is the PID module. Let me see if you can see my screen. This is my screen. Let me think about it. This is only PDF. So this is the PID. Okay. I think it's probably a good idea. I do this one, the screen. Yeah, the screen. Share the screen. Okay, so let's start by reviewing what we did last time. Let me see again, make sure you can see what I see here. Yes, okay, good. So do you guys know why we need to talk about Routh array? So that's because if you have a system and you have a polynomial, characteristic polynomial, so you want to check out if the system is stable or not. So you don't have a computer, you cannot solve all its roots. So there is a way to do it. It's called the Routh-Hurwitz method. So you need to memorize how to construct this table. The first table is one after another. Okay, the first table s to the power of n, an minus 1. So you skip an minus 1, then you have an minus 2. Let me see. This, so it's n and n minus 1, n minus 2, sorry, so skip this one. So this first row and the second row is highest order, next highest order. Then you can put all these coefficients line like that. So basically you need to know how to put first row, second row. Okay, the rule is simple. Then the third row and onwards are the same method. So how to do a B1 here is basically you do an minus 1 times an minus 2 minus this is the cross product. It's opposite to the determinant, remember? And we divide it by a minus 1 here. Okay, be careful. Okay. So these are very important skill, okay? How to construct the Routh table. You should memorize it. It's a very important skill. But after you did that, so how are you going to tell the stability of the system? So basically you need to check the first column. Is there any sign change? Remember, until s to the power of 0, okay? So basically it says that to be stable, then all your coefficients must be positive, same sign. All negative is fine, right? So all the elements in the first column must be positive. There's no sign change. If there is a sign change, it's not same sign, then your system is unstable. But how many unstable poles? It's called number of successive sign changes in the elements of column 1. It is already. So we're going to run through examples, okay? So you got a closed loop transfer function, okay? Remember, closed loop transfer function is usually you get this one like like a C controller, a plant, 1 plus CG. Okay, giving C, giving G, you get this. But we usually use a symbol as T. Okay, sorry, T. T is a closed loop transfer function. So do you need to draw a Routh array? You don't, because based on the condition 1, the system is immediately unstable because there's a one sign, not all positive. Okay, so this guy is negative. Without doing anything, the system is unstable. However, you cannot tell how many roots are. So this is all positive is called necessary condition. Okay, so let's go back. So these are necessary conditions, but it's not sufficient. You have to check the second. So this is necessary is not satisfied, then it's unstable. So let's check an example. So this is a closed loop transfer function, and this is called characteristic polynomial. You usually need to solve its roots, but it's very difficult to do by hand, solving the roots of a cubic, a third order polynomial. It's very difficult. You can do quadratic, but not third. It's difficult. So what you should do is, this is a an. This is an. An minus 2 is this one. N minus 2. Let's skip this one. So S squared then is the first one. An minus 1, and that's 1. Then an minus 3 is this one. So an minus 1, an minus 2, an minus 3. Okay. So based on that, we are going to check what's this. And all others are just 0, okay? You just put 0 in here. So what I get is 1 times 4, okay, 1 times 4, minus 3 times 2, divided by 1. 1 is this guy. You get a minus 2 here. So this guy is minus 2. And C1 here is, we can do the same idea. But how about this one? This one is like a 2 times 0 minus 4 times 0 divided by 2 is 0. Okay? So you can pad zeros here, okay, if you need it, until you get the last row. So this is S1. S0 is corresponding to here, then C1, I do this one minus this one. So B1 times 2, 1 plus multiplied by times 0 divided by B1. So that is the C1, okay? I will get a 2 here. So you can see from this first column, and you have 1, 2, 3, 4. Okay, so you have a sign. They are not the same sign, so the system is unstable. So this one, although all the coefficients are positive, as opposed to this one, so clearly, as I said, it's a sufficient. It's a necessary, not sufficient. Necessary. Right. Necessary, but not sufficient. So it's necessary, but not sufficient. So this one said, oh, necessary is all positive, but does that mean this is still stable? We need to check the first column of this guy. So the system is unstable, but I want to know how many unstable poles. So one sign change from here to here, another sign change from here to here. So positive to negative, negative to positive. So we have 2 unstable poles. Okay. All right. So you may say, oh, of course there's a, but what if I give you an example saying that if this is negative, I'm just assuming that if this is negative, then how many sign changes? You have 1 sign change and just 1 sign change, okay? It's unstable, but you only have 1 unstable pole. So, but right now we have positive in here, so then you have 2 sign change. Make sense? We can verify that is in MATLAB, okay? We can verify this one in MATLAB very easily, okay? So there are some cases called marginal stable system. So you have a pair of poles on the imaginary axis. So this is called how we are going to do in a row of zeros. So for example, you have something 0 in here. So let's still do this position servo system, okay? So you have speed, then integration, you have position, feedback controller using this transfer function. I decide what is the range of my k such that the system is stable. So the closed loop transfer function is G1 plus GH is 0. So this is my characteristic polynomial. So it's basically I have feedback controller, which is H times G plant and 1 plus HG fence. So then you have 1 plus HG is like this. Then you cancel this one to, so then what's left is this one plus this one. So this one plus this one. You arrange the terms, you end up with this one. So in fact, it's difficult for you to answer the question, what's the range of the k such that the closed loop system is stable? So that's why it's very useful for Routh-table method. So in this case, we can do this. So f an is 1, n minus 2 is this term, skip this one, 2. I don't have anything here, so you put a 0 in here if you want. Then s squared term, you have 4, so an minus 1, an minus 3 is 5, so this is also 0 here. So we can do this one. So you got 12, and you have positive 4k minus 5k, you got 1k left. So this is B1. Again, if I do this, so nothing left, okay? Nothing left. So it's 0, 0. Let me go back a slide and remind you of one thing here. So how you do the B2, okay? The B2, you still start from AN, okay? AN minus 4, AN minus 4, okay? It's not like something on top of it. No, that's wrong, okay? You only do A minus 1, okay? Be careful, okay? Be careful. So if you do something, if you say, oh, is this one and this one, that's probably wrong. I think I showed you last one was not right. It should be 4 times 0, that's 1, 0 here, divided by 4 will give you this one, okay? All right, so next, we're going to do the same. This one times this one minus this one is 0, divided by this one, you have 5k left, okay? 5k left, this one's 5k. So let's check this column. We know that to be stable, then k must be greater than 0, okay? But on the other hand, the k has to be greater than, less than 12, okay? So this everything is stable, okay? Everything is stable. On the other hand, when you have k is 12, okay? The whole row in here will give you 0, okay? This one, the whole thing here is 0, 0, 0, everything is 0. So it's called the whole is a row of zeros only, how you are going to do. So then we can tell that when k is 12, the system is marginally stable, okay? So in this case, I can write auxiliary equation like 4s squared plus 5k is 0. That is k is 12. So you end up with this one. S squared plus 15. So then this is how you solve your marginally stable pose when k is 12. Okay. So the third pole compared to the coefficients you will get is -4. So it's a real pole at -4. So this is stable. So then you know that the whole system is stable. Then the range of the k is between 0, not 0, between 0 to 12. And it could be equal to 12. So that's my k range. Okay. All right. So we'll continue to study something we call first element is 0. It's possible the first element is 0. Okay. And then you have divided by 0 case. It's difficult for next one. Say, for example, you have something like this. So then you have 5 is 15, 25 minus 25. Then this is 0. Okay. So this is 0. Then what you do is just put a positive small value epsilon in here and study this. So because epsilon is small, then you know this is a negative. Okay. This is a negative. So this is a positive, this is a negative. So we have two sign changes. So positive to negative, negative to positive. Okay. So that's an idea. So you have two unstable poles in here. Okay. So this system has two unstable poles. Okay. So you can see Routh-table is kind of very interesting. And give us an idea of how to check the stability without solving all the roots. So if I ask you to do a full roots of this polynomial, it's a very difficult task without computer. But using the Routh-table, you can immediately tell all the roots are living in the left half plane or right half plane. Nice, isn't it? And it's in particularly, this K is called a gain. Sometimes I don't know how big the gain I should put. Then they can tell you how to put the gain. What's the valid range to make the system stable? So then you have an infinite many choices of K. So this thing is called optimal choice. What's the optimal choice? You need to give me more specifications like what do you want, such that I can pick the right K for you. I know my K is in this range, but how I can make unique choice of K. So that's a control design problem, okay? So we're not going to do root blockers in this class because from my engineering practice in the past maybe 30-some years, I never really used the root blockers to do my design, although it could be. So I'm gonna skip all this root locus design thing. I hope you do frequency domain nicely. You know how to do a body plot. But to do body plot, you need to know this complex number operation. I hope we have talked about this thing before, different quadrants concept, complex number operations. These are review of high school stuff, okay? We have gone through all this already. So basically, for linear time invariant system, you have transfer function like this. So your input is sinusoid, output is also sinusoid. And input-output magnitude, okay, is connected to GJ omega here. Okay, that's why you need the GJ omega. When you S is replaced by J omega. How many of you ask the following question? Why we replace S in here with J omega? I suddenly can talk about frequency response. That is, you assume that you have a harmonic cosine sign. It's a complex number. Then you have a output is also a complex number. So this was the same omega. Okay, so response to the harmonic input. Then if we do real parts, so it's a cosine, imaginary parts is sine. So you put in, then you have this relationship. Okay, because if you do derivative in here, like this one, what are you going to get? Is j omega to the power of n. Okay, power of n, like here. Okay, so we have learned this thing before about frequency response is the magnitude and the phase. Okay, so the phase is this, magnitude is this, okay, m and phi. So the output is written as the input magnitude times this magnitude and phi here. Okay, so what I call this is sine in, sine out. Okay, we assume this u0 is 1. Okay, so sine in and sine out. What is the output sign? The magnitude of it is m. M is frequency dependent of the magnitude. So we plot this magnitude versus omega, we got Bode plot of magnitude, Bode plot. So these are just the example of oscillator. So you can see oscillator says you have, this is a resonance peak, okay, in the magnitude. This is called the resonance peak. Let me write down. Resonance peak. The reason is you have this omega 0 in here and go back. If you have this omega in here, it's possible that you can make this quoting 0. Because when your omega is choosing as the square root of this one, it's called, you make this one 0. So that magnitude is infinite. That's why you have this peak, infinite peak. Okay, so our resonance peak is here. And we use this one a lot. If I think I remind you about the specifications, rise time, percentage overshoot. This is called, we use this one as what we call second order model plant. Okay. Be careful. When we talk a plant model versus a model plant, it's a different. Remember, the term is called role model. Basically, I can use this one to serve as a role model to that, so that I design a controller to make my system to behave like this one. And the role model, we can specify a damping ratio omega n as I want, so that my system will behave like this. So the whole thing by this one is called model-based control, model MBC, model-based control. You have a role model, you have a plant model, then you design the controller. I'm going to go to that point later, okay? So we are going, oh yeah, we talked about bandwidth issue, and I think a long time ago, I talked about half power issue, why you have magic number 0.70, okay? That's called cutoff frequency. When you have a bandwidth, when you have a power dropped 50%, then that point is called bandwidth. Okay. Okay. I'm going to talk very important concept in here. It's called marginal stability or margin of stability. Okay. Or stability margin. Although the system, everything is good, it's working, it's stable, but we should think about stable versus stable different, because like how far away I'm from so this part is unstable, This part is stable. So I'm stable here. I'm also stable here. I'm stable here. But you can see my distance to unstable boundary is different. So I'm bad about writing here. But I think you know what I mean. It's about how far away you're from being unstable. So that's called stability margin. How can I tell? How can I tell? So giving G, giving H, how you can tell? Okay, so we need to introduce a very important concept. Okay, so first of all, because the whole loop transfer function is the G times H, I want to understand at what frequency the gain is 1. Okay, gain is 1. You remember gain is 1, then it's a 0 dB. Okay, 0 dB. So if I draw a Bode plot, so this is 0 dB. So this is the magnitude of L, loop transfer function, magnitude of it. Then you do a 20 log of 10. Okay, so so then if you draw a Bode plot, so you cross this point. So at this point is we called omega gain crossover GC. When omega is omega GC, then this is the magnitude is 1. Okay, it's 0 dB. Is here, this point. And there's another point is the phase is hitting minus pi. Okay, because phase, if you draw the phase usually start from 0. Okay, 0 degrees. Okay, because DC gain is a constant, so it's from 0, then you eventually go down and then constant. But of course, this usually we did first order system is minus 90, but there are, say for example, tau s plus 1. We know this transfer function. If this one, so this one will go to minus 90 degree, right? Okay, so this is linked to the omega. Okay, this is called bandwidth or cutoff frequency. So if I do squaring here, you can see this one will draw down like minus 100, okay? Minus 100, but asymptotically, okay? So it will never true, okay? So well, if I put 3 in here, then you are going to have something like this. So then you are going to cut, you are going to cross the minus 180 degrees. Then you have omega in here. So this is omega. So that omega is called phase crossover. Okay, gain crossover, phase crossover. Okay, all right. So remember you have, but what if you're you never cross the 180? It's possible. So then we call this is no crossover. So it's the infinity. It will be infinity. It's not going to cut it. Okay. So this concept is linked to the quiz problem I'm asking you to do. But now let's talk about this. This is a Bode plot. You know it. We're talking about corner frequency or cutoff frequency or break frequency about this. Okay. So it is interesting whenever you see a gain crossover, corner frequency here. If you put FB in here, this one is what? This one will give you J1 plus 1, okay? It's J1 plus 1, remember. So that's why you have a square root of 2 magnitude, and square, you will have 2, okay? So that's half, that's the half power of the signal. Then it's 45 degrees. So that is a frequency. You write in the magnitude versus phase. Okay. If you put the corner frequency there. So therefore, in a low pass filter, you remember 1 plus tau s plus 1. So you end up with, so everything is here is 0 dB until to a point you have a minus, this is a minus 20 dB per decade. So, but what is this frequency? This is what we call corner frequency. This is my corner frequency. And how to compute the corner frequency is like this. Okay, you make this term 1. Okay, make term 1, or you write something like this: 1 divided by S divided by omega C plus 1. So when omega is omega C, so in this case, omega C is 1 over tau. Okay, 1 over tau. Okay, 1 over tau. So the omega B is 1 over tau. Okay, 1 over tau. And remember, omega is 2 pi f. Okay, 2 pi f, or 2 pi divided by t. Okay, so you have learned this before. So this is just a review of symptoms. Okay, we have seen this already. But remember, I want to give you an interesting thing here. So this is a symptom for the dashed line, and here is the real line. What is the value in here? Value here is minus 3 dB. I explained this one in the class. Why this is minus 3 dB. This distance. And of course, this is corresponding to 45 degrees. Okay, this is again. This is for a simple. Oh yeah, this is not from 0 dB because k is not 1. Bode magnitude. We talk about second order. You have a resonance peak. Otherwise, you will have different behavior like that. But remember, the slope here is minus 40 dB per decade. Okay. So today, this is very new concept. Again, we need to answer about how to check the stability and gain phase margin. So what I told you here, if you have this total loop is minus 1. Minus 1 means the magnitude is 1. Or you have an argument is a argument of this GH, or you can write this one as an angle GH. Okay. If this one is minus 180 degrees, so we have seen that. Okay. So this is a point. Okay, this is a point. When is the omega? So that omega is called omega gain crossover. Gain crossover when it makes this 1. So at the gain crossover, okay, what is the gain crossover? What is the phase? Okay, so we're talking about phase margin first. So phase margin is when the gain is 0 dB. What is the phase? Say, for example, I give you an example here. So I have this is a 40 plot. So I have gain crossover here, omega GC. At this GC point, this is 0 dB. So this is at this point, okay? Then I want to check my, so this is a minus 80. So I want to check what is so is it 0 degree all the way until here. So I want to check what is corresponding to omega C. What is the phase in here, distance from here to here. So 180 plus this one. So this one is negative. So this is what's left. This is phi m. Okay, this is phi m. So this is called phase margin. Remember, the system in this case is called stable. Why? Because in this closed loop, the signal will never reverse. Okay, never reverse. It's always get attenuated. Only when you have 180 degrees, this is a phase crossover. This is a crossover. This one here, you can see corresponding to here, what's the gain? Gain is from here to here. This is the distance of the gain, okay? So this one is called gain margin, okay? This one gain margin. And this one is called phase margin. The gain margin is when you cross the 180 degree line corresponding to that gain margin. So in this case, gain margin is less than 1, okay? Because it's negative, okay? Negative dBs. It is less than 1, that means you have a closed loop system. Your signal going through the system coming over here, although it's reversed sign, become a positive feedback, reverse sign, positive feedback, but the overall gain is attenuated. And then you do attenuation. So the thing here I write is called stable. The system is stable. The gain is less than 1 while you cross your sign. Okay, while you cross your sign. Right? Does it make sense? Okay. Then, so basically I'm explaining that when you have omega cross at the minus 80 degrees, this one. This is the minus 80 degree. At this one, what is the omega? This is called omega PC. Okay, omega PC is this point. Omega PC. Phase crossover. You cross over this line called phase crossover. This one is called gain crossover, GC. You cross this 0 dB line. You cross when at the omega here. So then we say that's the dB, okay? That's the dB. So this one is definitely less. So this guy is definitely less than 1, okay? Because everything is. So then we call this is a gain margin. It's less than 1. This is less than 1, okay? 1 divided by gain margin. Okay, so that one, this one will be considered as how much. Basically, absolute value of this dB. So how much amplifications I can add to make the system unstable or greater than 1. So that's the dB, okay? That's the dB we have, okay? So basically, it's like sign here. Basically, we are saying here, what is the distance in here in dB, okay? Okay. So this is the distance in dB, okay? Or you can just do a 20 log 10. This is the dB and put a negative sign here because we don't want to say negative dB. So this is the distance from my system to be, you know. So remember, if I increase the system gain or if I reduce the system gain proportionally, is as if I'm bringing this one down, I reduce my gain, okay? So then my omega GC is here. So my system actually is even far away from the unstable boundary. So, but if I keep increasing my gain, then my loop will be like this. Then this is my cross gain here. So you can see that while I cross over, because I increase the gain, my phase will not change, okay? So you can see crossover 180, then this is greater than 0. So that means I have something come over here. This is greater than this, and when I plus it, remember it's negative feedback. So you have a 180. So then this get amplified until you explode. So it's unstable. So if you increase the gain to here, this system is unstable. Because you cross over here, you beyond 180. So, then all corresponding to 180 here, gain omega phase crossover, then this is my new gain margin. So that gain margin is negative. So the system is unstable. I know this may be very confusing, but that's the definition about. So I'm going to show you the system. So it's actually I showed you here. This is a 180-degree line, and you gain crossover here, and you phase crossover here. Omega p is phase crossover, gain crossover. So then this distance is called phase margin, and then this dB positive. Okay, this dB distance from here to here is dB is called gain margin. So gain margin, phase margin. Okay, phase margin. So that's for this is called Bode plot. It is possible that you can put the magnitude input and the imaginary and the real part. Let me show you one thing you can see. You have 1 divided by tau s plus 1. If I draw Bode plot, you know the Bode plot is something like this. Okay. It's from 0 dB to a point, then you go down, and this one is 0 degree, then you have minus 90 degrees. So you will never hit 100, 100 minus 180, never hit. So the omega GC is infinity. So in other words, I put a system in here, I put a KP in here, I close the loop, okay? Okay. There's a reference. So I want to know what is the range of my KP such that the system is stable. The answer is if KP is greater than 0, any KP is okay. Okay. You can check using Routh-table, Routh-table, or from analysis of gain phase margin. Okay. So, but for this is a Bode plot. So what if about Nyquist plot? So this is real, this is imaginary. So when omega is 0, then this thing is 1. So this is 1. Okay. So this is G. Okay, this is 1. Okay. When omega is infinity, is 0. Okay. So the whole thing will come over like this. Okay. Because the phase, any angle, any omega, the phase is always negative. So, okay. So this is my case. Okay. But if I do this one, I'll do a square. So you can imagine that I'm going to starting from here again, but we end up this way. Okay. To 0. Okay. But what if I have 3? Just starting from here, going to this way. What I have 4? So yes, I can still do here. Okay. Okay. But when it is 4, there's a problem. Okay, let me see. So there is something called -1 J0 point. So basically it's called -1 J0 point. So this -1 J0 point is exactly like you have a magnitude is 1, you have phase angle of this thing is -80 degrees. So from here to here is -degree, right? So that is the critical point in Nyquist plot, okay? Next plot. Okay. Next, the theorem saying that if you don't encircle this one, the system is stable. But somehow you have something like your system like from here, okay? So somehow you encircle this one. This is called encircle. It's inside of this encircle. This system is unstable. Why? Because while your phase at certain omega, while your phase is minus 180, then this is greater than 1. This is 1, okay? -1, okay? This is a greater than 1 magnitude. So then the system will be bigger and bigger, bigger and bigger in a closed loop setting. Okay, bigger and bigger. So it's unstable. But if you are somehow your system is something like this, it's outside your circle, not in circle or in circle. In circle. So this is actually called a Nyquist, how to read the system is stable or not using a Nyquist plot. So basically, what you do, you do a unit circle here, okay, unit circle, okay, unit circle, to see if it's inside the unit circle here, crossover, then the system is stable, and the distance from here to here, how far away from this one, okay, it's called uh, gain margin, and the angle in here is a phase margin angle. When you have this one here, when we first hit the 1, this is like gain crossover. This is phase crossover, okay? So this omega phase crossover is like here, okay? So this point corresponding to this point. This gain crossover, this point corresponding to this point, okay? And the angle in here is a phase margin, okay? So the phase margin we can compute, okay, the phase margin. So I'm drawing two, so this is an example of the oscillator. I'm not going to go through this one. Let's go through this one, stability using a Bode plot. Bode plot. So this is a magnitude plot. So this is 0 dB gain crossover. This is minus 80 degrees. So this is a phase margin. Then the phase crossover frequency is here, corresponding to this distance is called gain margin. This is phase margin. So this whole system is stable. Okay, it's a stable system. Unstable system is you already cross over. Okay, your sign changed basically, but your magnitude is still greater than 1. Amplified. So you got amplified feedback, amplified again, then your system unstable. So this is unstable. Or you say that you gain crossover. When you gain crossover, you start to be less than 1. But now you already passed 180 degrees. So you already passed. So from here, you can see the system is unstable as well. So I hope you understand what is gain margin, what is phase margin. Okay. Okay. So the reason we talk about margin is usually talking about for a stability, already stable case. Okay, stable case. The margin means how far away I'm from being unstable. So for an unstable system like that, talking about margin is already meaningless. Make sense? Okay. So similarly, the previous two Bode plots, these are two Bode plots. We draw in a Nyquist plot, imaginary real. So you can see this is a stable case, your intersecting point. So this is called a critical point, okay? This is a unit circle or unit circle, okay? So in this case, this is encircling this point. This is not encircling this one. So if you encircle this one, the system is unstable. So you can see Nyquist theorem is consistent to what we argue here, okay? It's not hard to understand. So we have an example in here. So you do Bode plot, then you do a Nyquist plot. So you can see I show you first order is something like this. Now they have something like this. here. So what does that mean? That is because of this numerator, 0 behavior here. Okay, that is due to that. Then we can do this. I think everybody knows this one already. Body plot and asymptotics. So basically, Nyquist stability is in circle. If you in circle, this is called in circle, then it is unstable. So basically, they say if you have eigenvalue, remember you have eigenvalue or characteristic polynomial right half plane. This is about the roots, characteristic roots. So this is unstable. Unstable, showing this is a mapping to Nyquist stability. So that's why you have an encircling problem here. Okay. So Nyquist stability theorem, that's abstract setting, but you only need to remember what I just told you about encircling problem. So this is called critical point -1 J0. Okay. So this is called number of unstable pole in this. Then they have a relationship like that. It's hard to memorize. So let's just use encircle problem, okay? If you encircle it, so in this case, this is A is unstable, B is stable. So although there is something here, but they didn't encircle it. So it's something like this. So it didn't encircle it, okay? Didn't encircle it, okay? But this case is unstable. For this system, you know, you have multiplicity 2 in here, so this system is unstable, okay? But a system like this one is, you have 0 in here, that is stable. I think I did something wrong in here. I should say, this is, so they did this way, sorry, they did this way. Then encircle it, then coming back, okay? So it's something like this. So this is also considered an encircle, okay? This corresponds to this. So this is unstable, this is a stable example. Control system compensation, so we are not going to talk about designing of this compensator yet. We are going to talk about PID control instead. So like, this is not a PID, okay? So this actually called lead, lag, compensator, okay? Lead, lag, compensator by choosing proper alpha and tau, okay? So you can use that one to basically to, let's say, let's use the word massage. So you have without, so this say this is 1, okay? This is 1. Your body plot, something like this, okay? You don't like this, so you want to massage it so that it will something like this. So you want to massage it, so that is the way to do it. So to change this solid line to the dashed line, you know, this so in the modern control, this is also a more general term. It's called loop shaping, meaning I have some ideal shape of this open loop body plot, but somehow it is not, I have a desired shape, but you are not in my shape. So I hope I can get something, the shaper, okay, to make you to be consistent with what I want. So this is called a compensator, okay, compensator. So when you do a lead compensator, you have A is between 0 to 1. It's called lead, okay. And similarly, when a greater than 1, that is lag. Okay. So we're going to skip this part. Okay, we're going to skip this part. So I just gave you a massage. What's the massage behavior? Yeah, you can see. So if you didn't do anything here, so you are going to have an uncompensated. The original one is something like this. Okay, something like this. This is the original Bode plot, but somehow I don't like it. I want this one to gain cross like this. So you add a lead compensator, you will have something like that. And lag, so then shape will be different. So to change the behavior, okay? So let's go back to what we are doing here in terms of our syllabus. Remember, today is our week number 9. Okay, week number 9. I'm planning to finish all the control topics today, but our viewers, they only have 15 minutes left. That's no good. So I have a deck of slides I want to go through, and you can see it's 86 slides. I have 15 minutes. So what we're going to do is to briefly talking about this and all the details you are going to walk in the spring break. And that PID part, I'm going to give you take-home midterm exam. So that will help you to go through or force you to go through all the PID stuff. So this is a very good deck of slides. So let me go through the quiz questions for you. So reference input. So this is a picture you feel sick about it, right? You see it all the time. That is our reality. We are going to see this again and again. Okay. So reference is one of us. This is unit step. C is a proportional controller. Proportional controller in here. KP is a constant. Okay. You have system with a relative degree of 2 minus 1. Relative degree is 1, but what is the system type? 1, yes. Then I want to understand, because now it's more complicated. I want to understand what's my range of KP, okay? So what's the range of that? Do you know how to do this? So that you choose, what's the range of the KP, the gain you choose, such that using Routh-table, you can check the range. I'm pretty sure KP must be greater than 0, okay? All right. So you are giving H is 1, C is 1, GS is just this one, right? Just this guy. What is the gain margin for this? It's infinity. Because you don't have a phase crossover, so you don't have a omega p in it. So it's infinite. So what's the phase margin? Okay, the phase margin. The phase margin is because you have a gain crossover, do you? Yes, you do. Do you? It's always 0 dB, don't cross the 1. So probably when you do a crossover, the phase margin is considered as also infinite. Because you don't have a phase margin here, okay? You didn't cross the 0 dB line. You are from the 0 dB line then going down, right? So now I tell you about this one, and what is the gain margin? Do you cross the minus 80-degree line? You don't, right? So phase margin, a gain margin is infinite. What's the phase margin? Did you cross 0 dB line? I don't think so. You didn't. So this is also infinity. You know what is a PID, right? You know what is AWBT, you don't know yet. I'll tell you. You know what is MAD, right? Modeling, analysis, and design. So I'm going to tell you two of these things. Okay. Then we finish today's lecture. How about that? So PID stands for proportional, integral, and derivative. So I want you to see an important thing here. Say, for example, you have a reference. Can you see this? Let me see if you can. Yes, you can. So So have reference, of system output, feedback, then you do a model analysis design, you make a decision, and then you have a control action. But remember, when you put the control action to the plant to be controlled, you should remember your control authority is always limited. If unlimited, that's God, okay? So be careful here. Even if they didn't say explicitly there's a saturation, you should consider there is a saturation, because you cannot assume I have an infinite power to apply to the system. So you may damage the system. Make sense? Okay. The controller I'm doing here may not be a PID, but I just tell you that in general, there's an actuator saturation here. Okay, and this saturation usually will give us trouble if we don't consider it carefully. So if we do PID in here, okay, if we do PID in here, the integrator inside the PID will have something called integrator windup. This is not called wind, it's called wind, like circled, wind up, okay, wind up. I'm going to give an example of this wind up phenomenon, okay? So if we have a step response, so this is my PID, the I component. Let's assume I limit my control signal from minus 0.1 to positive 0.1. Of course, this is purposely limited to small on purpose to see how it goes. So you can see that the system will, because the error is too big, the saturation will be triggered. So the system initially is got, because the initial error is very big, so then it will be triggered as saturation. Then this is always above 0.1, right? So you can see that it will continue straight until to the point the I goes down, okay? And then you again get a saturation. So it's always a saturation. Then eventually you will come out of the saturation. So this is get out of saturation. So this thing, pointer. So this thing is called winding, okay? Winding. After you wind so many times, you get out of the saturation. So we also sometimes call, hey, this is deeply saturated. Then you get out of the saturation, then system looks normal. Okay. So that if you don't consider any strategy, that's called real life, you will meet with this, okay? I have a story to share with you that I have a PhD student spent 3 months on this thing. He didn't realize, he didn't learn about integrator windup. He didn't know that there's a limit about your voltage applied to a ground mobile robot. So when he do the robot control, the robot will spin, 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 then start to go. So that spinning is because of this thing. Spin and spin, so positive spin, negative spin, positive spin, negative spin, then eventually start to move, okay, as we want. So that transient is very strange. And he got stuck on this thing for a long time. I didn't realize he didn't know what is the integrator windup. But unfortunately, this thing is not covered seriously in any textbook. So he wasted 90 days in summer research and tried to solve this problem without knowing this integrator windup. He tried to do troubleshooting for a long time. Cannot solve it. So wasted a summer. That means his professor was not well informed about this thing, okay? But you guys are lucky, I'm telling you. So this is the reality. If you don't know the anti-windup, you are going to live with this. So let me show you using anti-windup scheme. Although you still limit your control, so you are going to have something like this. You can see your response is nicely, you don't hit too much. Then, isn't this nice? Of course it's nice. And of course, initially your controller is saturated, so you have a straight line going up. Hit this one, you just come back without some ugly behaviors like that. And it's a real life. My PhD student in Utah State University wasted 90 days in summer because of this, because he didn't know this block diagram. This block diagram is called anti-windup. And everybody in my class, if you say you took control with Dr. Chen, you have to know this. And you can even draw this block diagram with eyes closed. So you should do that. So without this thing, so this thing is called anti-windup scheme. So this is the input, is output. This is saturated. So then a saturated thing is smaller when the actual thing. Actual is the big one I saturate. So when I'm in saturation state, when I'm not in saturation state, so this should be 0, okay? When I'm in saturation state, this one is bigger than this one. So this is a negative. I pulled out negative times a coefficient, put it here, negative. It's just like I pull out the controller input, integrator's input, so that I get out of the saturation as quickly as possible. So of course, this is a D, this is a P, proportional control. But why you have a minus Y in here? Where is my R? Okay, R, dr, dt, R is a constant, okay, remember? R dot is 0, okay? R dot is 0. So then here is a Y dot only. Makes sense, right? So that's why you only need to do minus Y in here. So again, so pull out input, output, make a difference. And so this is the saturation arrow. Then make this one come back. So with this term, it's called anti-windup. This is P, I, D, PID with anti-windup mechanism. Okay, windup mechanism. So now we come back to this one. So AW stands for anti-windup. If you have a system with a saturator and an integrator, you will always need anti-windup mechanism. Without that, your robot will spin in place for 30 days, for 90 days. There is at least one example, and I experienced in my previous student. I thought he knows this thing, but he didn't. So too bad. And then when he understand everything about this, he feel very sorry about it. Yeah, he should take my control course. So it's very effective. Okay. Of course, depending on the gain here, the behavior will be different. So if TT is infinity, means this is 0. Okay, it's the bigger, the smaller. Okay, so the bigger as if you don't have. So the bigger you have a bigger T, you have bigger velocity here. You have bigger transient. Okay, if TT is infinity, means you don't have anti-1F. So there's a rule of thumb that 1F coefficient should be half of the integration coefficient. Okay, and or some people say, oh, it should be like geometric mean of TITD for PID. Remember, I'm using TITD. This is called traditional form. Okay, I'm go back to this point. I'm doing this. So KP is in front. TD is like this. So TI is like TD is this. Do you guys know what's going on here? Because this T and this T cancel out, so it's dimensionless. And this T and this DDT, this T and this T will cancel out. Okay, cancel out. So this T and this T cancel out. So there's nothing to do with T in here. So because this is nothing to do with T. So E, this term, they have the same dimension or unit. Okay, make sense? Otherwise, E and E dot, they are not the same unit. One is position, one is the rate, position meter per second for E dot. One is meter. So meter per meter per, this doesn't make good sense, right? So that's why I love this term, okay? PID. Of course, you can change to other formats. So please go through this deck of slides, and you may wonder what is BT, AWBT. So AWBT is called, this is anti-1F. There's a bumpless transfer. It's called bumpless transfer. AWBT, bumpless transfer. So this is saturation, this is PID. So you add, you add on top of this one, your anti-1F. This is anti-1F. Okay. Then you add this term in here to make it bumpless transfer. It's called bumpless transfer. Okay. This bumpless transfer is usually when you are in manual mode, switch to automatic mode. Okay, bumpless transfer. So that's for AWBT, bumpless transfer. Ziegler-Nichols tuning rule. Ziegler-Nichols tuning rule is related to our this ZN stands for Ziegler-Nichols. Okay. So basically, what you do is you have a system you want to control. You want to put a P or PI or PD, but I don't know how to put a K and TI/TD there. Okay. So deciding these three parameters is called PID parameter setting. Okay, parameter setting. How to do that? So remember, you want to design a controller, you have know the structure of the controller, but you don't know the parameter. Okay. So then we need to answer the question about what do you want and what do you know. Okay, what do you know? So what do you know about the system? Say, I don't know anything about my system except I can do a reaction curve here. Okay, so this is delta U is my input. The reaction curve is the red one, and settled, the steady state is delta Y. So delta Y to delta U will be Kp, and theta is L divided by T is my delay versus my time constant. So then this is called AOT and DC gain. So this KP is like DC gain, KP. So DC gain and this theta. Theta is something like a nominal delay model. Okay, nominal. It's kind of normalized delay. So you have KP and theta. You can read from this reaction curve. These magic numbers 1.9, 1.2, 2, 3, and 2, and divided by 2 here. So these coefficients are decided by these two gentlemen in 1942 and first published in ASME journal. Okay, and I'll upload his original paper for you. You can check. And they did exhaustive summary of existing control loop, how they are already in operation and how they will decide on those parameters. They did summarize it. So this is kind of heuristic empirical type. Okay, there are numerous, like more than 1,000 papers, thousands of papers after Zygmunt-Nichols. People try to refine or polish this Zygmunt-Nichols PID tuning table. Okay, I even did something on that, published that, so you can check my work. So we are going to meet on the April 1st. So whenever I say something on that day, don't treat it as a joke. It's real. We are going to meet 2:30 of April 1st. After this class, I'm going to send you guys the midterm exam. We don't have a homework today. It's already given you from yesterday, last week. So I think everything is on track. The only thing is you budget time and put in effort. So let me try to see if you have any questions before we finish here. Go ahead, unmute yourself. Can you unmute yourself? Let me see if I can chat.
So when will the due date of the exam be?
You mean the midterm exam?
Yeah.
How about I give you 2 weeks? So this is March, this is April 1st. How about April 8th?
Okay.
Okay, I give you 2 weeks, okay? So you cannot accuse me of destroying your spring break. So, all right. Okay, so I count by 3, then I'm going to close if you don't ask me anything, okay? So 1, 2, 3. Then goodbye and take care and following the rule and be safe, be healthy, okay?
Have a good one.
Bye-bye. Bye-bye.